What we're going to do in this segment is we're going to take a look at the individual components of the gas turbine engine, and we're going to begin with a walkthrough of a gas turbine engine, and this is actually that of a turbojet. So on the video, what you can see is as you go from the beginning of the gas turbine engine, you start at the compressor stage. And so the air would enter in, and there we will have a series of rotors and stators. And you'll notice that the thickness or the height of the blades is getting shorter and shorter, smaller and smaller as the air compresses. So we will go through the compression process. It's a multi-stage compression process on axial flow turbines, as we're looking at here. And then you get to the point where you leave the compressor stage and you then move into the combustion or the combustor. And essentially what these are, they call them tin can combustors that are wrapped around the perimeter of the gas turbine engine. And within these combustion stages, you would have mixing and you would have fuel addition and combustion inside. You're trying to minimize hot spots. And then, so you're dealing with a very high pressure gas. It's been pressurized because of the air. It's combusting, so it's very hot. So you have high pressures, high temperatures, high enthalpy flow. That then moves along into the gas turbine, and that is where you're extracting some of that enthalpy and getting work out of it by rotating the turbine. And so the turbine stage is the final stage. You could have one stage, two stage, three stage, multiple stage of the turbines, but typically fewer than you would have for your compression stage. So that is a quick overview of the gas turbine engine. What we're going to do now, we're going to take a look at component by component, taking a look at what each of these look like. And we will begin with the compression stage. So the compressors, or the compressor I should say, typically we're dealing with multi-stage, and I'm also talking about axial flow type. There's another type of gas turbine engine that uses a centrifugal compressor at the front, but we will not be considering that here. We'll be talking about multi-stage and axial flow type. And typically what you could see in the video, it's referred to as being a cascade. And here what you'll have are compressor blades that are very thin, and you'll have a stator row. They call it the stator row because it's not moving, it's stationary. And that is followed by the rotors. These should all be identical. There we go, that one's a little better. Now the rotor is rotating. And so it's moving in this direction. The stators are stationary. Now the velocity coming in of the air, and we're compressing air, would have V naught. That's usually the first stage. And the velocity leaving would then have a velocity that is typically tangential to the trailing edge. V1 would be the direction. And then what we do, we superimpose the velocity of the rotor, which would be omega, the rotational rate, times the radius. And that would give us a relative velocity. And so if you take a course in turbo machinery, you'll draw a lot of these different vector diagrams as you look at each stage of the process. And then when you leave the rotor, again, you'll have V2, and you'll notice now we're at station 2. So we start at 0, then 1, then 2. Again, you add on the velocity due to the rotation, and you will get the absolute velocity for the air coming through would be in a direction like that, for example. Now, typically, what the compressor consists of is basically a series of well-designed diffusers Because what we are trying to achieve, we're trying to achieve a pressure rise across each of these stages. And that's what a diffuser does, gives you a pressure rise. So it's providing a large static pressure rise without large total pressure losses. Now, where could you get large total pressure losses? It could be from things such as shock waves. And it could also be due to boundary layer separation. You do not want to have separated flow. That's where the boundary layer detaches from your airfoil within the compressor cascade. And so those in themselves will result in pressure losses. We want to avoid those. And so that is the compressor. And the next thing we'll do is we'll move on into the combustion chamber. So the combustion chamber takes the high pressure air that was coming out of the compression stage, and we mix it with fuel, and then we initiate combustion. So that's what the combustion chamber does. It's taking our high pressure air from the compressor. We try to minimize the amount of loss as well as hot spots. And they're essentially tin can combustors. So let's take a look at what one of these might look like. If you were to cut it open, you might have something like this. Now, quite often the technology within the combustor itself is proprietary, depending upon the particular manufacturer of the engine. Because they're trying to do things with the combustion process to minimize pollutants such as NOx, or that's nitrogen oxide, or other types of things that you might get as byproducts of combustion that are environmentally not desirable. So what we have coming in here is our air, and that has been compressed from the compression stage. We will then also introduce a small amount of fuel, so that's mass flow rate of fuel coming in. And I show these, it's like a double can thing, but you have secondary jets coming in here of some of the air coming in from the side. And the purpose of the secondary jets is to provide a lot of mixing and reducing the hot spots that you may have. And then there are different ways that they will use to maintain the flame in this combustion region. So sometimes there's a swirl combustor where you get a vortex, and the vortex has a induced velocity upstream, and you can kind of hold the flame there. Other times what they'll have is kind of a bluff body here, and the wake within the bluff body is what maintains the flame. Different technologies depending upon the vendor and the engine fabricator. So that is the combustion chamber within an engine, and then eventually what will happen is the exhaust gases leave here, and what you try to do is have a uniform temperature distribution at this stage. Now, you're not always going to get that. You'll have some hot spots. The reason you want to minimize the hot spots is you do not want hot spots on your turbine, or that point of the turbine blade will exceed the rated temperature of the turbine blade itself. So with that, let's move on to the final stage, and that is the turbine. So with the turbine, what we're looking at, and we're talking here again about multi-stage and axial flow, but we're dealing with high inlet temperatures, and consequently we need to consider heat transfer and cooling of the blades. And we either do that by material science, that is using high temperature alloys and different types of coating, aluminum oxide, ceramic coatings, and we also do it using heat transfer. And for that, what we do is we take bleed air from our compressor and we use it to cool the turbine blades. And so looking at a schematic of the turbine itself, it looks something like this. And again, we will use the vector diagrams that I talked about earlier for the compressor. Now the turbine has a lot more curvature than the compressor, and you can see that by looking at the blades themselves, which I'll show you a video of in a second. Again, I apologize for my horrible artwork, but here we have stator, so that would be a stationary row, and then we have the rotor, which would be a row that is rotating. And so here the rotor might be moving in that direction. Again, we use velocity diagrams, looking at the relative velocity from one stage to the next. So what the turbine is doing, it's converting high pressure and temperature gas, so high enthalpy fluid, into work. So what I'll do now, we'll take a quick look at a video with an actual turbine blade, and that gives you an idea as to some of the cooling mechanisms that might be within the turbine. So let's take a look at that. This is the blade from a gas turbine engine, and what you're looking at here, this is the leading edge of the gas turbine blade. Looking at it from the end, you can see the cross section, and so it's a very curved shape. Unlike traditional airfoils like you'd see on an airplane, this is changing the direction of the flow going through the turbine quite significantly. The other thing to notice, there is a bit of a bluish white coating, and that would be a coating to protect it from the high temperatures that would be encountered within the exhaust gas stream of the gas turbine engine. And the other thing to notice is that there are a number of ports on the bottom of the blade where it would go in to the engine itself, and compressed air from the compressor would be used and ported through that ducting system, and then it would come out through these small ports. There's some on the leading edge, there's some up on the tip of the blade, some towards the trailing edge, and then even on the tip you can see there are more ports there. Those are used for cooling the blade due to the hot combustion gases, and that is the gas turbine blade. So you could see from the turbine blade that we had a coating on it, and really that is the area of increasing the efficiency. There are a number of different areas. You have the combustion section, you also have the performance of the compressor, but in terms of the turbine, places where we can have efficiency enhancements are in terms of enabling the turbine blade to take higher and higher temperatures. So going on a scale of looking at our exhaust gases, typically gas turbine gases in the exhaust are anywhere from 1300 degrees C to 1450 degrees C. And you can have efficiency improvement as you basically have your gas turbine blades able to tolerate larger and larger temperatures. So if we're at around 900 degrees C, that's what we get with internal cooling. It's somewhere in that ballpark. So these are the places where the efficiency of the gas turbine engine is going to increase. It comes with a little bit of a challenge though, because as you get to the higher temperatures, you can start getting NOx formation. So NOx is NOx that we will look at when we consider combustion, and you need to be careful there because that is a pollutant. And so then that would come back to the engineers working with the combustion chamber, and they would have to do designs there in order to reduce hot spots and reduce NOx formation. So these are the balancing acts that people that do gas turbine engine design would be involved with as they try to drive the thermal efficiency higher and higher.